Welcome to WikiPodcast. You know that moment when you hold a warm mug, feeling that comforting heat spread into your hands? Or maybe you felt that blast of hot air stepping off a plane in a tropical place? We all experience heat. It's everywhere.
We do. But that everyday feeling is really just scratching the surface, isn't it? It's our perception of something much, much deeper.
Exactly. What is that sensation? Is it some kind of invisible fluid flowing around? Or is it something more fundamental, like tiny particles doing a chaotic dance?
That's the heart of it.
Yeah, it's wild. They couldn't just, weigh it or measure its length. They were looking at its effects. And surprisingly, some early thinkers had ideas that sound, pretty modern.
They really did. We're talking 17th century here.
Cool.
People like Francis Bacon in England, he was saying pretty boldly that the essence of heat is just motion. Tiny parts moving inside things.
Galileo, too, right. He saw it as something we feel, a sensation caused by particle movement.
And Robert Hooke, Robert Boyle, they echo that. Heat is the motion of the bits and pieces that make up an object.
I love that quote included from John Locke back in 1720. It paints such a vivid picture. He said, "Heat is a very brisk agitation of the insensible parts."
Insensible parts, meaning the parts too small to see or sense directly.
Right, and he used examples everyone would get, like rubbing a brass nail until it gets hot, or wagon axles catching fire from friction, motion creating heat.
That really nails the early heat is motion idea. But it wasn't the only game in town, was it? For a long time, it was up against this other theory, heat as a substance, a fluid.
Caloric theory.
Caloric theory, yeah. And you can see the appeal.
Totally. You touch something hot, it feels like hotness flows into you. A drink cools down, it seems like something left it. It's very intuitive.
It is. And some early experiments, especially those trying to avoid friction, seem to back up this substance idea. For a while, anyway.
But then things started to shift, especially when friction and work got involved more directly.
Exactly. Late 18th, mid-19th century. That's when the mechanical theory really gained ground. It brought work and friction into the picture, leading towards how we understand heat now.
Okay, and this brings us to something I found really fascinating in the sources, the point where scientists finally clearly separated heat from temperature.
Yes. Crucial distinction.
It sounds obvious to us, maybe, but back then, they often used the terms interchangeably. It wasn't really sorted out until the mid-1700s.
And that separation is just fundamental for physics today. Heat, that's a quantity of energy being transferred. Temperature, that's about the intensity, the hotness.
So how did they start teasing that apart?
Well, early experiments started hinting at it. Brooke Taylor, 1723, he mixed hot and cold water. He noticed the final temperature depended not just on how hot the water was initially, but how much hot water he added.
So quantity mattered.
Implicitly, yeah. Suggested a quantity was involved. And then William Cullen, 1748, did this cool experiment, literally, evaporative cooling with diethyl ether.
Oh, yeah, lowering the pressure made it boil and get colder, right?
Yeah.
Without adding outside heat.
Exactly. Sure, temperature could drop because of a phase change, not just heat removal.
Right.
It got people thinking.
And that influenced Joseph Black, his student,
Yeah.
whose work seems absolutely central here.
Absolutely groundbreaking.
Yeah.
Black did these careful experiments mixing things, like equal masses of different stuff at different temperatures. Think water and mercury, the classic example.
Okay.
If you put the same amount of, let's call it heat energy, into a kilo of water and a kilo of mercury, their temperature doesn't rise the same amount.
So the same quantity of heat causes a different change in temperature depending on what it's heating?
Precisely. Black had this great example. Picture a hot stone cooling down by heating up some water. Same volume. Maybe the stone's temperature drops 20 degrees, but the water only goes up 10 degrees.
Okay, got it.
He realized different substances had a different, he called it capacity for the matter of heat. We call it specific heat capacity now.
And the sources said he used a unit, degrees of heat. But it wasn't like our joule today. It was more context dependent, like temp change times mass or temp change times time.
Right, it was proportional, a way to quantify the effect.
Yeah.
But his really famous discovery, around 1757-ish, was latent heat.
Latent heat. Okay, this is the big one.
Yeah, it's the heat absorbed or released when something changes, phase melts, boils, freezes, condenses without the temperature changing at all.
He noticed how long snow took to melt, even on a warm day.
Exactly. He realized a ton of heat was being soaked up just for the melting process itself, not for raising the temperature.
In that experiment comparing heating ice versus water, that really shows it.
It does. Heating ice at 0 Celsius just to melt it took way, way more degrees of heat as he measured it than warming the resulting water by several degrees.
So melting the ice absorbed something like 140 of his degrees of heat, but warming the water by 8 degrees only took 8 degrees of heat. That heat during melting was hidden? Latent?
Perfect.
Yeah.
Hidden, latent. And that led to the terms. Sensible heat, the heat you sense as a temperature change, and latent heat, the heat involved in phase changes.
And later on, people like Joule connected sensible heat to the kinetic energy of particles, the jiggling and latent heat to potential energy, like pulling particles apart.
That's the modern connection, yes.
Yeah.
Kinetic for temperature rise, potential for phase change.
And recognizing heat as a quantity led straight to building the first calorimeter, didn't it? Lavoisier and Laplace.
The ice calorimeter around the 1780s. Designed specifically to measure the quantity of heat by seeing how much ice it melted. A practical tool to nail down that difference between quantity of heat and degree of hotness.
Okay, so bringing all that history together, how do we define heat in thermodynamics now?
Simply put, heat is energy in transfer.
It's not something an object has, like mass. It's energy moving.
Exactly. Moving between a system and its surroundings. And crucially, it moves via microscopic mechanisms.
Like what?
Like conduction atoms jiggling and bumping neighbors. Radiation energy carried by electromagnetic waves, even friction at the micro level.
And this is different from thermodynamic work.
Very different. Work involves macroscopic mechanisms, a force moving something, a piston being pushed. Heat is the microscopic, often more chaotic, energy transfer.
The first law of thermodynamics ties these together.
It does. For a closed system, it basically says the heat you add, Q, goes into changing the system's internal energy, all the microscopic energy inside, or it allows the system to do work, W, on its surroundings, or both.
So Q equals U plus W heat is one way energy crosses the boundary.
Precisely. It's a way to account for energy changes that aren't explained by macroscopic work.
And the unit is the joule, like other forms of energy, though we still see BTU in calories sometimes.
We do. And it's interesting, you end up with these sort of complementary definitions from history. The practical one, heat, is what a calorimeter measures, and the theoretical one, heat is the energy transfer that isn't work, derived from the first law. Both are useful.
Okay, and just quickly, the ways heat actually moves, the mechanisms.
Right, the main three. Conduction, direct contact, energy passed particle to particle.
Like a panhandle getting hot?
Exactly. Then radiation, energy via waves, like sunshine warming your face.
Yeah.
Doesn't need a medium in between to get hot itself.
Right, space is cold, but the sun's heat gets here.
And convection. This is heat transported by the bulk movement of a fluid, liquid, or gas. Hot air rising, ocean currents. The fluid itself moves, carrying its internal energy along. Often works with conduction or radiation.
Makes sense. So let's circle back to where we started. Heat is motion. How does that old idea stack up now with modern physics?
Amazingly well, actually. Those early thinkers were really onto something. Kinetic theory, statistical mechanics, they absolutely confirm heat transfer is fundamentally linked to particle motion.
But it's not just the motion in the object, it's the transfer of that energy.
Exactly. It's the transfer of microscopic energy, kinetic, and potential driven by temperature differences.
Because hotter things have more energetic particles, and they bump into slower ones, sharing the energy.
That's the essence of it. Countless random collisions and interactions leading to a net flow of energy. Statistical mechanics describes this beautifully. Heat transfer is associated with disordered microscopic actions. Random jiggles, vibrations, particles jumping energy levels.
As opposed to work, which is more ordered.
Right. Work involves microscopic motions that are coordinated, leading to a macroscopic force and displacement. Heat is the random, diffuse energy exchange.
Okay, so let's tie it all together. Heat, temperature, and that feeling of hotness.
Hotness is our basic perception, that comparative sense. Hotter, colder. It tells you which way heat will flow, naturally, from hotter to colder.
And that hotness is what a thermometer measures, giving us empirical temperature, a scale for that feeling.
Pretty much. Even for complex systems, without a single defined temperature, you can still talk about relative hotness determining energy flow. So understanding heat as this energy in transfer driven by microscopic chaos, it connects everything. Why your coffee cools down, how engines work, how the sun warms the earth, it all comes down to that transferred molecular energy.
So you've just taken a deep dive into what heat truly is. It's not just a feeling, not some mysterious fluid. It's fundamental energy transfer, deeply rooted in the ceaseless, chaotic motion of molecules.
It really is a fascinating journey, seeing how our understanding evolved from just feeling warmth to grasping the underlying microscopic dance.
And thinking about that dance, it does leave you with a big question, doesn't it? If the heat we feel, the power in an engine, the sun warming planets, if it all stems from countless tiny particles just randomly jiggling and bumping around, how does that fundamental, messy microscopic motion manage to scale up and produce all the complex, organized, and sometimes incredibly powerful effects we see all around us in the macroscopic world?
Thanks for listening. Write us your opinion in the comments on how the microscopic motion of molecules explains the macroscopic feeling and effects of heat. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.